Stop relying on the revision shortcut that is literally destroying your physics grade. Seriously. Every year, thousands of students walk into their Cambridge 9702 solid-state physics exam thinking they can just bluff their way through the fundamentals of materials with a couple of memorized one-line definitions, and it completely backfires. The very second you're asked to connect macroscopic theory to macroscopic applications, that fragile list of facts just shatters under exam conditions. Just picture it. The exam timer is ticking down. You turn the page and see a standard, predictable question about semiconductor properties. Your heart rate spikes. The grade boundaries for this paper are incredibly tight, and right here is exactly where most students bleed 2 easy marks. Why? Well, it's because they confuse simple, everyday labels with actual scientific explanations. They completely drop the ball on the exact terminology that Cambridge examiners are practically begging for.
Let's look at a super common and honestly painful assumption. Semiconductors conduct electricity just like metals, but worse. No, absolutely not. This is the exact flawed assumption that costs students their top band grade. Ordinary revision fails here because it just doesn't capture the actual depth of the solid-state system. If you treat a semiconductor like it's just a bad metal, you are entirely missing the underlying physics of energy bands and atomic arrangements.
Okay, let's dive into Section 1, the mark scheme framework. We need to use a concept development framework that turns those easily forgotten facts into usable, high-scoring understanding. Here's your very first quick win. A macro topic in solid-state physics should absolutely never be reduced to a simple one-line definition. Instead, apply this 3-part model directly from your textbook to organize your exam paragraphs. Ask yourself, number 1, what is the structure or process? Number 2, why does it happen? And number 3, what observable effect does it actually produce? This beautifully structures your answer around mechanism and consequence. It ensures you're linking the microscopic cause to the macroscopic effect every single time. And this builds right into the elite exam writing framework you absolutely need to secure those top band marks. You're going to start with the core concept, right? Then support it with evidence or data if the question gives you any. After that, apply your scientific reasoning. And finally, wrap the whole thing up in precise examiner wording. This 4-step sequence guarantees you're hitting the Cambridge assessment objectives instead of just, word vomiting everything you know and hoping something sticks. Moving right along to Section 2. Holes and carriers. Let's get into the core physics of charge transport. Look, we literally cannot talk about solid-state materials without mastering specific vocabulary. The most absolutely crucial point here is understanding what a hole actually is. It's a highly useful physical model representing the absence of an electron. Let me repeat that. It is not merely a bookkeeping trick or some neat mathematical convenience. In a lot of electronic materials, the concept of a hole is just as important as the motion of the electrons themselves. If you don't explicitly state this dual nature of charge carriers in your exam, you are simply not getting the mark. Which brings us to the basics of charge transport. The properties of a material emerge directly from how its atoms are arranged and bonded. This arrangement dictates the allowed motion of charge carriers and the energy structure of the material, and that ultimately results in usable conductivity. A strong exam answer is always going to link a new term, like charge transport, to a measurable or observable property. Now, in a moment, I'll show you the examiner clue that changes the answer completely. But first, you need the framework that makes that clue obvious. Hang on to that thought, because without this next piece of the puzzle, that clue is going to slip right past you under exam pressure. Let's hit Section 3, Insulators versus Semiconductors. In the exam, when you're asked to compare these two, you've got to state both sides using matched language. You can't just describe the semiconductor and leave the insulator implied. They hate that. And this brilliantly illustrates the exact comparison you need. For insulators, they are passive. Their energy band structure is completely locked, preventing carrier motion. But for semiconductors, they allow for conductivity control, making them the active basis for electronic devices. This distinction is so meaningful when discussing band structure because it shows the examiner you truly understand why some materials just sit there passively while others form the actual foundation of our technology. All right, Section 4, Live Answer Transformation. Let's do a little Spot the Error challenge. Okay, it's time for an interactive viewer challenge. We're going to do a topper autopsy here. Listen to this incredibly flawed student answer. The material is a semiconductor because it has conductivity. I want you to literally pause and predict the error. Why does this answer score 0 marks? Got it? It's because the student is confusing a basic label with an actual explanation. Just stating that a material has a property without linking it to the atomic arrangement, the bonding, or the carrier motion is a classic trap. Now, what's really fascinating here is that this actually reveals the critical examiner clue I teased earlier, the constraints. Students constantly lose the final top-tier marks in these larger questions because they totally forget to mention vital physical constraints like temperature, purity, structural order, or external field strength. A semiconductor doesn't just spontaneously conduct. Its conductivity is highly dependent on these specific external variables. Let's transform that average sentence into an A-grade sentence using our layered framework. Compare that flawed answer we just looked at with our top band correction. Specific band structure allows thermal excitation at standard temperature to create holes, yielding usable conductivity. Do you see the difference there? We included the structure, we included the constraint of standard temperature, the mechanism of creating holes, and finally the observable effect. That right there is exactly how you secure full marks.
Next up, Section 5, Real-World Applications.
When you're writing extended exam answers, bringing in realistic applications provides that sweet final evaluation mark. Why? Because it proves to the examiner that you know why the concept matters beyond the textbook page. Think about it. Semiconductor devices underpin literally all computing, communication, and control systems. Band behavior helps explain solar cells, LEDs, sensors, integrated circuits, the whole shebang. Choosing a material for switching or insulation depends entirely on understanding carrier motion and allowed energies. It isn't just disconnected theory. It is the absolute foundation of modern technology.
Which brings us to Section 6, Final Strategy and Quick Recall. Listen, you need to be able to reduce this entire macro topic into trigger statements that you can retrieve instantly under high stress. This is your 1-minute drill. In less than 60 seconds for absolutely any solid-state topic, you must be able to do 4 things. 1. State the defining idea. 2. Name one mechanism. 3. Detail one observable property. And 4. Give one real-world application. If you can't do this drill smoothly yet, you need another cycle of active recall, because structured, disciplined prose based on this exact drill is always going to score higher than an unplanned, panicky list of facts.
But honestly, this leaves a massive, unresolved problem. What happens when you turn to the last page of the exam, the time is running out, and you face a completely unfamiliar application or some complex data analysis that you have never, ever seen before? How do you prevent that sudden exam timer panic from wiping out all the structural frameworks we just built today? Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Seriously, to conquer that exam timer panic, you absolutely need a bulletproof time control system and a deep awareness of common traps. You've got the frameworks for solid-state physics now, but ask yourself this. When that clock is ticking down, are you going to rely on memorized labels, or are you going to command the physics? Check out our next explainer on time control to lock in your A grade. I'll see you there.